Okay, good afternoon. My name's Anthony Lynn. I'm here today to talk about the legacy of scientific code. Does it change? No. It was changing. Told you I'd get it wrong, didn't waste time. So what am I going to talk about today? I'm going to start with an introduction of why am I talking to you about legacy code? How did that end up happening? And just what is it meant to do? Then I'm going to talk about something called failing fast. The idea of actually, let's cut my losses, move on. And the key thing here is to actually also learn fast. Then the power of iterative improvements. So just making things a little better, but a lot. Do it lots and lots and lots. And then useful tools that I found for doing this, and finally some conclusions. So how did I end up working with legacy code? At the start of the year, I was asked to work on the quasielasticbayes package, which was originally a Fortran code. And it's quite old now. You can see the paper on the side. It's from 1992. I wasn't even in school yet. So it's pretty old, but it's now available on Python as part of PyPy, so you can go pip install it and play with it, or at least the exposed part. And the Fortran code, it's all Fortran 90 extensions and hasn't changed for many years, so we can consider it to be relatively stable in that respect. So what's the point of this piece of software? Well, in quasi-elastic data, we get things like, nope, pointer's not going to work for me. So we get things like these plots here where you've got your peaks. And what you want to know is, well, what are the parameters? I want to know my background, my offset for the center, the elastic peak, and then some inelastic features. In this case, we have Lorentzians. So I'll be using Lorentzians and inelastic features interchangeably. And the results from this code are generally accepted by the community to be correct. Yay! Now, here's where the tricky bit comes in. And yes, I'm going to ask audience participation. So prepare yourselves. So the top is a fit with 1 Lorentzian, the middle 2, the bottom 3. Now, can people please put their hand up if they think 1 is the correct number of Lorentzians for this data? We got like 4 people. 2. About 4 again. And 3.
Did you say 4?
Who thinks it's 3 Lorentzians? I think it's conspiring. It's been about 4 people every time. Well, that's about what I expected. You know, I've been working with this data for the best part of a year and I can't tell them apart. Couldn't tell you which one was right. The code tells me it's 2. And it does this by using some Bayesian statistics to say which one is the most likely given the data. So it's not necessarily the best fit. So what's the problem with all this? We're just making mountains out of molehills by complaining about it. Well, actually, there's a few issues. One, we don't know what it's actually doing. People can't tell you this is what that code does, this is how it gets that answer. It just does. And the paper's no help because it just verifies the results. It doesn't really talk about the method or how they got there. I can't just ask the author. You know, this is 30 years ago. They're long gone. They've retired, I think, but certainly not at STFC. That lovely Fortran 90 extension, not so great because inside it's the style of Fortran 70, so continues, go-tos, and all those other things that make you not want to look at code anymore. So this has all led to some issues. So compiling this code is actually quite difficult these days, particularly on Windows, because it breaks so many modern rules of Fortran, the compilers just say, no, I don't want to do this. And so if you look at our Git repo, you will find a zip file which contains a compiler that we have to unpack, install, and then run to make our unit tests work. Not ideal. So we'd like to not have to do that. And also, to top it all off, if you run it on Windows and Linux, you get different answers. And if you ask people why, the answer is, I don't know. They're similar-ish, but why? So basically, issue of working with legacy code, well, I'm sure many of you are familiar with this. They're not documented. They're not maintainable, not particularly readable or commented because the scientists wrote it. They wrote it to do a job. It worked. They were happy. They did the paper. They moved on. they didn't write tests for it, they didn't document it, because that would have wasted time when you could be working on their next research project. And as this fake book cover suggests, the guy who wrote it's gone, and oh dear, it's everywhere. We're very reliant on this. And so when you ask around, there are a couple of people from that paper still at ISIS, and I've asked, what's this code do? And the answer I've got is, no, which is very unhelpful. So a big part of what I've been doing is actually trying to understand what this code does. And so that brings me to failing fast. And here's a snippet of the Fortran. So if you look on here, you'll see some terrible things, but not the function name. So you're just going to have to believe me when I say it's BIMBLR. I have no idea how you pronounce it. I just call it Bimbler. Does no idea from that name. The variable names are awful. You got things like WX. What's that? I don't know. Also, if you look at the bottom, it closes a file, but it never actually opens it. So if you run this out in the wrong order, my code's going to crash. Also, what have I actually changed in here? What variables are different? I don't know that either. This is not helpful. So what did I do? I wrote it into Python because it's easy to develop in Python. You can do it quite quickly. And I kept as much the same as possible. So my Fortran arrays became NumPy arrays. And I added a few comments as I worked stuff out, such as W something meant it was an input, whereas something B meant it was an output. So that was good. However, we then got weirdness because you'll see I've circled a -2 and a -1 on the Fortran. And this is because Fortran counts from 1, Python counts from 0. So there are lots of random -1s hanging around. And this doesn't sound so bad, but it gets very confusing very, very quickly because you got to include these -1s or you'll just start counting in the wrong place. You have to remember, actually, this index that I've been given as an input was expecting the first thing to be 1, not 0, and it's not fun. So here's my first attempt at that, dealing with that. So you can see the range is I'm in -1, and then I've got a 0, -1, and another range. It's just not fun. And as I say, confusing. So what I did was about a day's work. I went, you know what? This isn't going to work. I'm just going to cut my losses, start again, knowing this will be a problem. And my solution was completely to change how the code worked. And I created some code to make Python look like Fortran. So I could pretend it's Fortran. So I had a vector class, a 2D matrix, and a wrapper for get range, so that I can now put the exact same numbers in as the Fortran, and under the hood, that magic class will just sort it all out and I'll get the correct thing. Great. And I could put more comments in because I'd seen this code before. I'd seen how it fitted in with some other things, so I had a better understanding of its context. So that allowed me to deduce what some of it was doing. And to make sure it was correct, at the end, I compared it with Fortran. So I took the results of this, I hacked the Fortran to spit out some numbers into a file and just made sure they looked relatively similar. But then I ran into another problem. There are a lot of globals in this software. You can see here, and this is one of the smaller ones, it's got quite a long argument list. And this became difficult to work with. And again, after about a day or two, I got to a point where it's kind of, this is ridiculous, and decided I'm starting again. So let's get rid of all of that and do a new version where I hide all of these globals into a class, technically a dictionary of classes, but it makes it a lot neater. So now my bit you can't see at the top just says comms, LP file, and I think there was a third argument that I can't remember. And this sort of neatens it all up because now we can see where all those globals are more easily. And again, because I'd seen the code 2 times previously and its context 2 times previously, I knew a bit more of what I was doing. So I could add a few more comments. The I/O for Fortran is very different from Python. And the way it behaves is very different, which was inconvenient. So I decided, actually, let's change it so that they behave in a similar fashion. So what I did is not start again completely and just went to the beginning of code and just replaced where it was doing the changes because it was relatively unintrusive because we didn't actually write to file that often, but it gave me the opportunity to say, I'm looking at this code yet again. I know a bit more about what it's doing, what it's supposed to be doing. Let's update it. Let's add more comments. Let's improve it. And then another thing I ran into, Fortran can silently convert a matrix into a vector, which is very irritating until you realize that's what it's doing. And again, with this one, I didn't have to start again because all I needed to do was change the way a matrix works under the hood so that it was actually a vector, and then add some methods so I could access it, write to it, read to it, those sort of things. But again, I went through the whole code from scratch, just reading it and adding comments and adding those details of the understanding I've gained from having seen it so many times before. So you can see now I've got things like, oh, I think this is the X bins, I think these are the Y bins. Another issue I ran into is Fortran will silently convert between complex and real numbers. This is one of the reasons the compiler doesn't work, by the way. So I created methods to allow us to compress the data into a complex from reals and to stretch out complex into a list of reals to replicate that behavior. So once I had this good understanding of what was going on, I could then use proper names. So this snippet actually has decent names. So we got Y data in bin and sigma data in bin. I won't give prizes for guessing what they are. So it's a lot easier to read. It's a lot easier to understand what's going on. And I could just completely delete the old function because the old function name is datin1. But I decided not to do that, instead to add a deprecation warning via a decorator and then have it call my new function. Because unfortunately, I'm not finished. There are other inelastic features that I'm going to have to work with. And to make my life easier when translating those, I'm going to use the Fortran names. So I've still got it, rather than having to try and remember which one was datin1. So here's a more complex example. And you can see the very long list of globals I was complaining about before. We've got strange variable names again, such as xbmin. And we've got subroutines such as bimble, or however you pronounce it, and xginit. Again, no idea what that is from that name. And the dreaded continues and gotos. So we translated it. Turns out, bimble is actually a rebin algorithm. So the new thing we call is called rebin. And the xginit was actually just removing background. So the new function is called rm background. So again, a lot easier to read, a lot easier to understand and work with. But I only got there by having seen the code many, many times in this context, many, many times. So things I found useful for this, because Fortran versus Python, Python's going to be a lot slower. So something that helped me was a tool called Cython, which has really good profiling and is very easy to use. So here you can see an example. So we do a couple of imports. We have the Cython profile equals true. And then we just sort of wrap it in this function call. So the QL data, blah, blah, blah. That is the function I would call if I didn't want to profile it. I would just do that bit. And then a couple of lines afterwards. And then it prints out something like this. I've completely cheated. And this is actually working out pi, the code I've profiled here, just because I wrote it badly on purpose to get decent numbers. So you can see here in our table, we have number of calls, total time, and the cumulative time. So if you look at the top one, you'll see the cumulative time is 105, but the total time is much smaller. And that's because it excludes the function calls within it. So it allows you to see actually what is the real culprit here. So if we pretend that that first one wasn't so bad, you would say, okay, let's look. So I'm going to check on here. It's gen data is the next biggest culprit for time. So I know to go look at that function, try and speed that up. And then we can run the profiler again and then check actually what needs doing next. So that's really helpful. And given how easy it was to use, I'll be doing it again. However, that's not all. In Cython, you can also create sort of pseudo C code or C++. So there's an example here of some pretty colors. And you can see that we've got type definitions via cdef. And we've also got them in the arguments for our functions. So it's a lot more similar to C++. And it compiles as well before you actually put it out. And if you know Python or C++, it's actually quite easy to learn. And all of these yellow highlightings is actually from one of the outputs, which shows you this bit is slow. This is the bit you need to work on to make it faster. So it's really helpful for actually spotting those bottlenecks as well in your code. So to conclude, it can be difficult and time-consuming to work on legacy code. And I think those of us who have done it all agree it's more like a prison sentence some days than a job. But it's important to be open to the idea of failing fast, saying, actually, this isn't going to work. I need to do something different. And sometimes that has to be quite drastic. But iterative improvements are a great way to actually make progress with that. Because if you make a minimal set of changes, you're unlikely to break things. And then you get understanding from the context, having seen it again and again and again and again. And you know what's coming. And ultimately, the reason we did this was we needed understanding of the code. I can't tell you exactly what it does, but much better than what we had. To solve the compiler problems, well, Python doesn't have that, or Cython, and to understand the OS dependency. And that comes from rounding errors, actually. And Cython can be used to help with profiling and speeding up Python. And there's a link to our GitHub, and that picture once again. Thank you.
Thank you for the excellent talk. Do we have any questions for our speaker? Oh, please go ahead.
Well, thank you for the presentation. But I'd like to warn against what you did. There are many people who are complaining, especially in the Fortran community. I don't know if there are many people writing Fortran here around, that well, Python is killing our planet because of the resources it needs to run. And well, by rewriting Fortran code into Python, basically you are consuming a lot more energy than what it was used to consume when running in Fortran. Maybe the best would have been to translate Fortran into another language which was of equivalent level, maybe C, maybe C++, and the code would have been simpler and would have had the same performances as the initial code. So about maintainability, I believe C has a, let's say, a brighter future than Fortran.
Okay, so I'm just going to repeat the question a bit in case. So the question basically revolved around Python is very resource heavy and isn't so great for the planet when compared to a pre-compiled language such as Fortran or C++. And the reason we went with Python is in this first instance, we wanted to get understanding quickly. It was more about the speed of my learning as opposed to the speed of the code. So in the future, we may go back and say, actually, this is better in C++ or better in some other pre-compiled language. But all the extra boilerplate required to actually write in that pre-compiled language in the first place would have slowed down the understanding and learning that we needed. And that was the priority.
Thanks. I think we have time for one more question, please.
I think it's a bit facile to mock old code. This is 30-year-old code. Maybe you could spare a thought for people who manage to write useful code with such primitive languages and tools and so on. At the time, there was no internet, no revision control for these kinds of projects. There was no collaboration that meant that you had to make your code follow certain rules. People exchanged code freely as a favor. So, you know, what will today's code look like in 30 years?
No, I apologize if I cause offense, but compared to modern standards, it's not what we do. And I will admit, you know, my PhD and postdoc days, I wrote damn awful code. And I am ashamed that it's that bad, having looked back, because I didn't do unit testing, I didn't do documentation, I didn't do comments. All the things I complained about, I did, basically. And yes, it's because you don't know better in a lot of cases. And technology and paradigms change. You know, things like, it used to be a good idea to make a big software package that could do everything. Now it's better to make lots of little libraries. It's just the changing of mindset and learning.
That's because it can be combined with other people's work. In this case,
exactly,
there was no such mandate, so it's not surprising that they didn't overstrain themselves.
Yeah.
Something that they didn't need to do.
Well, thank you very much.